Hi, everyone, and welcome to Juniper's Virtual Summit. Thank you for joining us. My name is Savi Venkatachalapathy, and I'm part of the product management team at Juniper. In this session, I would like to walk you through our containerized routing stack that is deployment-hardened and cloud-native. Network operators are in more of a bind now than ever before to meet the growing demands of their customers and looking to introduce new services reliably and quickly to the market. To accomplish this, they are taking advantage of the cloud-native software applications which offer flexibility, scalability, agility, and simplicity. In their quest for there are only few options when it comes to cloud-native routing applications, whether it is feature-rich, capable of segment routing features in addition to IPv4 v6, end-to-end solution that's not tightly coupled with the underlying hardware. The current solutions available today are either proprietary vendor integrated solutions or open source software that comes with its own feature velocity and support challenges. So to summarize the requirements for a cloud native routing stack, it needs to be disaggregated from the hardware, deployment hardened with full feature set, high performant, and containerized. But why the emphasis on containerized routing stack? Let's drill into it. By virtue of being containerized, the application is lightweight, has small memory footprint, offers better resource utilization. There are multiple container runtime options such as Docker, Mesos, etc. Orchestration is simplified, taking advantage of load balancing, auto-scaling from Kubernetes, for example. The application itself is a lot of the times based on microservices architecture and can be upgraded in seconds as opposed to minutes. Also, containerized routing stack could be used to build a pre-prod simulation network to emulate the control plane behavior. With its small footprint, now you could do this with fewer servers than if you were to use VMs. So how is Juniper addressing these requirements? With CRPD, Junos containerized RPD. So what is CRPD? It's Juniper's routing and management stack packaged as a container. It is feature-rich, supporting IPv4 and v6, MPBGP, L3VPN, BFD, ECMP, weighted ECMP, rib sharding for faster BGP convergence. And CRPD also embodies the microservices architecture, deployed as a Docker container and integrated with Kubernetes or OpenShift for orchestration. It supports Linux Fib for IPv4, v6, MPLS, and SR. And since it is the same management stack that you would find on Junos devices, CRPD supports netconf, OpenConfig APIs, and YANG data models. And similarly, you can influence the routing decisions by programming the routes either through GDBI Open Standards APIs or Juniper's programmable RPD, which is also known as Junos Extension Toolkit APIs. All in all, CRPD is high performant, where you could scale up to 200 million rep when you're running it on a highly beefed up x86 servers. Some of the benefits of CRPD is that it is hardened, standards compliant, supports rich routing policies, BGP filters. It's fully programmable with OpenConfig PRPD APIs and lends itself for observability and monitoring with gRPC-based streaming telemetry of control plane sensors. For example, BGP information, session states, updates, notifications, route attributes, etc. Above all, it is supported by Juniper Stack with service releases for bug fixes, ongoing feature enhancements, and a predefined release cadence that's in line with Junos releases. Now, let's look into some of the use cases for CRPD. Routing on the host. Why would you need that? If you look at the server multi-homing compared with other proprietary options with CRPD, you get a standards-based eBGP protocol multi-homing solution, and this gives you better resiliency, redundancy in case of node failure. So servers are not limited to layer 2 networks only. You can expose layer 3 network connections, RIB to other applications that are L3 aware. Given that CRPD container is a container with small footprint, it can coexist with other applications sharing the namespace of the applications, or you can host CRPD on the host itself, where it shares the namespace of the host, allowing the host and all other processes across and access and control over the RIB. So here's an example of egress traffic engineering use case where CRPD could be used as an EPE functionality. So in case of EPE, we are talking about application servers at the edge, and these servers could be hosting different kinds of applications, for example, video streaming applications along with text and data applications. And you can program different egress routes, paths for the different application traffic, this way better utilizing the egress links and reducing the network congestion while maintaining the SLAs for that particular application traffic. CRPD runs on the servers alongside applications sharing the same Linux namespace. CRPD gets the best egress routes from the EPE controller and installs those routes into the Linux routing table to perform traffic engineering. The transport tunneling mechanism from CRPD to the border routers could be GRE or MPLS, and CRPD does the MPLS encapsulation to send the traffic to the correct egress peer. If the egress peer next hop programmed by the EPE controller is not reachable, then CRPD provides the fallback option of using BGP to calculate the best path without disrupting the application traffic flow. Furthermore, CRPD supports overlays on server, L3VPN verbs, maintains separate RIB per verb, and can potentially support MPLS over GRE, IP, and IP tunnels. Now let's look at another use case where CRPD is applicable. It is as a route reflector with scaled-out leaf-spine fabrics or Kubernetes clusters. Deploying CRPD as a route reflector solves the scaling issues that arise while adding a new iBGP node to networks that require full mesh iBGP neighbors. Additionally, CRPD can be used as a scale-out route server when deployed as Docker containers. So with a Docker bridge that has NAT enabled and connected to the host network interface, you can create multiple instances of CRPD behind the bridge and load balance across these instances for a better performance. As you can see in the picture here, CRPD instances RS0, RS1 are created with IP addresses in the Docker bridge, subnet 172.17.0, and sit behind the Docker NAT bridge. To the BGP clients R1, R2, R3, etc., the routes come from a single route server, and now this can scale up to thousands of BGP clients. Let's also look at another use case where CRPD can be deployed. So switching gears, CRPD can also be used as a routing stack on the network hardware that has Sonic running on it. In a Sonic environment, CRPD runs as a Docker container, and this can be used to replace the default routing stack container that comes as part of the Sonic package. In addition to programming the FIB in Linux kernel, CRPD also supports an interface to program FIB into the underlying switch forwarding ASIC. Using netlink integration with FPM SyncT libraries, CRPD programs the FIB into the Redis database, from where the Sonic SyncT agent then programs the ASIC FIB. The routing tables in CRPD, Linux kernel, and the ASIC are to be consistent. The host path here is supported via netlink interfaces. CRPD supports Junos style config for route protocols as well as operational show commands. CRPD is also MPLS and SR ready, which means that whenever Sonic ecosystem supports MPLS SR FIB, CRPD could be easily configured on the Sonic switch to provide MPLS and SR features. Use CRPD on Sonic to deploy an IP fabric in the data center or as a routing stack for emerging use cases like 5G cell site gateways. Juniper is going to maintain the hardware compatibility list of all the Sonic enabled switches on which CRPD has been integrated and qualified. Now let's look at the demo of running CRPD on a host or CRPD on a sonic switch, as well as the CRPD for egress peer engineering use case.
I'm going to talk about containerized RPD. This is a demo of CRPD on a server showing how a CRPD Docker container can be created and brought up in just a few seconds. Here we show a CRPD Docker container being active, and we can monitor its resource utilization. You will notice that we are using Junos CLI for configuration and operational commands. This is another demonstration of CRPD running as a Docker container. Here, we are using the Microsoft Sonic, ported to the QFX 5200 platform. Junos CLI is being used for the configuration and operational commands. We have RPD running and learning routes over a BGP session. These routes are programmed to Sonic. Sonic stores the routes and the route state in a Redis database, and these routes are eventually downloaded to the forwarding ASIC. We can also see RPD programming routes to the Linux kernel. This is a demo of CRPD acting as an ingress PE node in a BGP LU egress peer engineering topology. It's also called EPE. Here, what we have in the topology is a data center network, AS19, which is peering with multiple ASs which are advertising reachability to this host H1, which is having IPv4 and IPv6 address. CRPD is acting as an ingress node here, which is also having a v4 and v6 address configured. This is to demonstrate steering of both v4 and v6 traffic. We see that the peering router in AS19 is peering with the peers using multiple interfaces. And we have highlighted two peering sessions, 19101 and 19111. Between the ASBR PR1 and the ingress server, there is a GRE tunnel between 2020-2020 and 1919-1919. This data center network is an IPv4 only network. We are going to demonstrate a ping between the v4 and v6 addresses on CRPD and the host, which is going over BGP LU, that's MPLS over GRE. It's basically going to be v4 or v6 traffic over MPLS over GRE. The CRPD node is going to control how the traffic is exiting AS19 towards 19101 or 19111 by simulating a controller route at CRPD, which is going to have a static route at endpoint H1 with the next hop of either 19101 or 19111 or the IPv6 counterparts. So we are going to look at the traffic in TCP dump by looking at the Linux shell at server 2, that is node SVR2. We are also going to look at the BGP session state and RPD RIB state of server 2 and also the routes in the Linux FIB at server 2. So let's dive in. Here I want to show you when we are in the POD. We log into the Linux VM, which is simulating the data center servers, and here we are seeing that CRPD is running as a Docker container. We can log into this Docker container and we see the interfaces that have been configured on this Linux shell. One of them we have the GRE interface that I want to show you. So this has the remote and local endpoints as we described. And we can see the routes pushed by CRPD. The V4 routes and the V6 routes, which have the MPLS label, and it's going over GRE. So this is V4 over MPLS over GRE. And this is V6 over MPLS over GRE. And then we can get into the Juniper CLI and look at the routing state. The first thing I want to show you is the interfaces that CRPD has learned from the Linux subsystem. Here we can see the details of GRE interface. This is the interface that we have learned from the Linux and we are going to push traffic over it. CRPD is peering with the RRs in the network and talking V4 unicast, V6 unicast and BGP LU with the RRs. It's going to learn the service routes with the protocol next hop of the egress peers, and through BGP LU, it's going to learn the reachability of how to reach those egress peers. It is going to do the recursive resolution and send the traffic over. So we are looking at one of these routes in detail. Here we have many BGP routes and a controller installed static route, which is choosing a non-active route as the exit point. If we look at one of these BGP routes in detail, we will see that the route is received with a protocol next hop of 19111, which is being recursively resolved. This 19111 is learned using BGP LU, and we can see that we have learned the label 301168 through BGP LU, which are protocol next hop of 1919-1919 IPv4 map, IPv6 address. So the route for this is going over GRE. We have configured a static route in INET3 to resolve this protocol next hop. That is the protocol next hop for BGP LU routes to go over GRE. This is what tells CRPD that the GRE endpoint is reachable over this GRE interface. Let's go and do the ping. There's a ping running here, V4 and V6. We see these ping packets in the TCP dump. Basically, we are doing a TCP dump to match all the GRE packets on the Linux shell. We see here the GRE packet between 1919-1919 and 2020-2020, and we have the V4 packet. This is the reply coming in. It is non-MPLS. And the packet that is going out is the echo request. This has MPLS encap, and the ICMP request is inside the MPLS packet. IPv4 over MPLS over GRE here. And we can see the same thing for IPv6. We will just stop the V4 ping and have the V6 ping only running, so we can see the V6 packet here. We see the GRE header and the V6. There is a reply. And we see the GRE MPLS IPv6, so this is the outgoing packet. Now we are going to start the V4 ping also. And here I have two interfaces on which I am monitoring the traffic statistics. These are interfaces at the egress ASBR. There's 19101 and 19111. Right now, we have a controller route that is directing traffic towards this interface. We see the outgoing packets in this interface, V4 and V6. Now, I am going to roll back the route. I can show you what this static route looks like. It is just a static route which has the endpoint address that is internet prefix. And it has a protocol next hop as the egress peer, which RPD is resolving. So this static route becomes the API between the controller and CRPD, that needs to say what is the service prefix and which egress pair we want to direct the traffic to. The label does not need to be part of this conversation. So, the communication between the controller and the server is simplified. Now we are going to remove the static route, or you could change its next hop to point to a different exit point. It can go both ways. And now we will see the traffic shifting from this interface to this interface. You see, the traffic shifted to this interface. If we look at the Linux shell, we will see that the labels have changed. Earlier the label was 301184. Now it is 301168. We can put the controller route back in and we can see the traffic shift back. Traffic shifted to the other interface. All this is happening with just a route on the server changing. There is no routing changes on the ASBR or any other router on the network. So, just a controller is able to tell the server where to direct the traffic to, and it's able to do it. So we can see the route change in the Linux shell, and you can see that the route has changed only for the prefix that we changed it. For ::2, 777777 it remains the same old BGP route. The controller can do a targeted redirection of traffic for a certain flow alone at a certain server. That is what we wanted to show. This is a showcase of how CRPD can act as a companion for the other apps, which are running on the data center server. And the app just needs to share the Linux network namespace with CRPD and whatever routing information that the CRPD is installing in the Linux FIB. It can be used by the app by just following the regular Linux forwarding. So, this is a simplified way of deploying egress peer engineering in any data center. Thank you.
All in all, CRPD is deployment-hardened, feature-rich, containerized routing stack that enables plenty of use cases with either routing on the host or on the SONiC hardware. It deploys within seconds, lightweight, and cloud native. For additional information for collateral or demo videos, please visit our website. And if you like to give it a spin, please register and download the 90-day software trial software. Thank you.